Everyone, and welcome to my Lab 4 video report. In this lab, we are modeling many different circuits while recording voltage, current, and resistance. With these measurements, we can better understand how and why the loop and node rules work for closed circuits and how we can use them to solve physics problems. These circuits were simulated in a computer program called Circuit Construction Kit that contained ideal versions of tools to make and measure circuits in the real world, and this program was made by the Colorado Fed. And then for the first circuit, we made a simple series circuit with two resistors of 47 and 100 ohms respectively. And here we can find, using an ammeter, that the current through the circuit is 0.02 amps, which follows Ohm's law and the node rule, where you find the voltage divided by the resistance or is equal to the current, or there's other ways to rearrange that equations. However, it only applies to a closed circuit, so if you remove one of the ammeters, you do not have a complete circuit anymore. So if you measure the voltage there, then the ammeter is going to read 0, and the change in voltage is going to be 3 volts. Now, here's a graph of the change in voltage throughout the circuit on the previous slide, marked on points A, B, C, D, and so forth. And so as you can see, when it comes across resistor, you have a voltage drop on both of these places based on how large the resistance is, because voltage is equal to the current, which is constant, times the resistance. And so calculating those, adding those up together, gives you a total voltage of change in voltage of 0 across the circuit, which lines up with the loop rule for a closed circuit. Now, another thing is, if you set one of the ammeters to parallel, then you are avoiding one of the resistors, in this case the 100 ohm resistor, which, because the electrons choose to take the path of least resistance, and so the 100 ohm resistor is no longer included in the calculations, so you end up with a current of 0.06 amps instead of 0.02 because you have less resistance. Then the next circuit we tried out was an RC circuit, which is a circuit with a resistor, in this case a light bulb, and a capacitor. And here we've started experimenting with how long it takes for a capacitor to charge and discharge based on how strong the resistor is, and it looks like here that the charge time approximately doubles for and the discharge current also doubles based on the size of the resistor. In this next part, we started graphing the discharge of a capacitor over time, where if you use some algebra and some calculus based off of the loop rule, using the knowledge about the change in voltage based on a capacitor and the change in voltage from a ohmic resistor, you can find this equation here, the natural log of the change in voltage divided by the initial change in voltage equals negative t over RC, which is a linear relationship which can help us graph it. And if you notice here, for the component of our x, which is actually our t in this equation, would give us our negative 1 over RC, which is negative 0.167. So if we continue going through this, we'll go over how it's negative 1.67, which, solving for RC, gives us 5.988. We can also solve for RC because we know the values of R and C, the resistance and the capacitance, to be 300 ohms and 0.2 farads, because that's what we set them in the circuit. This gives us a value of 6. This means using the loop node to find that RC was very accurate, and the way our graph was very accurate, mostly because this was a model, and so it's following ideal conditions instead of a real-world simulation where a real-world experiment, which can be much more inaccurate. Now for some questions about how much more error would be encountered if we started doing this in the real world. So if you're using an actual ammeter instead of the ideal simulated ammeter, this would have an effect on the circuits you hooked up, because pretty much everything in the real world has resistance, and ammeters have some small resistance. So using the node rule, you would know that there was a non-zero voltage drop across the ammeter, which would modify our circuit in some way and throw off our results, because an ideal ammeter has zero resistance. And then if you're doing this lab in real life and used a real battery to charge a real capacitor without the resistor, our ideal model would predict that it takes basically no time to reach full charge. But in the real world, this is not going to happen because basically everything has some sort of resistance. Batteries have some resistance. The resistance to the wire would also play a factor, which did not in this experiment. And so this would all slow down the charge time. So hopefully you got a good understanding of what we accomplished in our lab, and